So, aloha. Lesson 6, two-dimensional equations. You know what? We're talking about collisions at angles. We're going to get there, but we're going to start off with, here's what I would consider a good physics 12 question that's still in a nice straight line. Example 1 says, a bullet is moving at a bullet is moving at 250 meters per second. It strikes a 5-kilogram wood block at rest and sticks into it. If the bullet and the block move together, A, write a momentum equation. Well, it's a collision. The sum of all the momentum before equals the sum of all the momentum after. There's A. B says find the speed. Okay, let's break this down into its constituent momentum parts. Before the collision, what's moving? The bullet, the block. You know what? Normally I'd use a B for bullet and a B for block, but since they both begin with B, I'll call this mass 1. I'll call this mass 2. So, before the collision, what's moving? Mass 1, mass 2, or both? Mass 1. Momentum of 1 initial. Wham! They collide. Make you jump. After the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Stuck together. Mass 1 plus mass 2 V final. We've got our setup, but now we have to pause. Ding, 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 ding. And we say, do we have angles in this question? Or is everything in a nice straight line? Is there a theta? Is there a north of south? Is there an east of west? You know what? Everything's in a nice straight line, so I don't need to dulp. I can keep going. Otherwise, I would draw a little picture and I'd be doing vector math tip to tail, which you'll see in a bit. What are they asking me to find? The speed of the block after the impact. I guess, oh, you know what? I already broke this down into mass 1 plus mass 2 V final, so I'm going to, in the interests of saving room, make this M1 V1 initial. That probably screwed up your guys' notes, but don't worry, we can get it on the next line. Because how would I get the V final by itself? Answer, divide. Divide. I'll get V final is equal to M1 V1 initial divided by the mass of both of them stuck together. V final is going to be mass 1, 30 grams, 0.03. V1, 250, divided by 0.03 plus 5. What's the final speed? Now, it does say final speed. I'm finding final velocity, but I guess if they just want the speed, I would give them the magnitude instead of a directional component. Okay. 0.03 times 250. You know what? 0.03 plus 5, I can do that in my head, divided by 5.03. And I get 1.491 blah blah 1.49 meters per second. There's the answer to B. C. Find the heat energy. Heat energy? Energy. Now, there isn't a change in height, but there is a change in speed. There isn't a yucky curvy path, but they're mentioning heat energy. I think this is a job for conservation of energy. I think I'm going to go kinetic initial plus potential initial equals kinetic final plus potential final plus heat. But because there's no change in height, I think those are both 0. So I'm going to get the heat by itself by minusing KE final over. I'll get this. Heat equals KE initial minus KE final. But I got to be careful. Initially, what's moving? Only mass 1. So the mass is going to be different in this term. After what's moving, this a half mv squared is going to be the mass of both. It's going to look like this. Heat is going to be a half m 0.03 250 squared minus a half 5.03, the mass of both, 1.49 squared. That's how much I lost to heat. And this is why momentum is so nice. It does allow us actually to calculate how much energy was lost fairly easily. Yes, it's a vector. It's trickier that way. 0.5 times 0.03 a half times m times v squared minus 0.5 times 5.03 times, answer button, squared. I get 932 joules. Oh, change colors, Mr. Dueck. You know what? It's heat. Let's do it in red. Heat equals 932 joules. That's how much heat was generated during this collision. Now, why is that physics 12? Because it combines energy and momentum. Why do I consider this a fairly straightforward physics 12? No angles. Everything's in a nice straight line. We said momentum works, conservation of momentum works great for collisions and explosions. It works great for juns. Example 2, an explosion. The diagram below shows two pop cans of unequal mass. Initially at rest, that's probably important. An explosive charge is detonated between them. Boom! And the cans fly apart. Oh, this is my favorite unit to teach. Hopefully you guys are awake now. What can be said about their velocities after the explosion? Using principles of physics, explain your answer. Did they say explosion? How might I analyze this? What tool might I use? What? Conservation of momentum. The sum of all the momentum before the explosion equals the sum of all the momentum after the explosion. Before the explosion, what's moving? Mass 1, mass 2, or both? Oh, neither. So what's my momentum before the explosion? 0. After the explosion, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Separate. Momentum 1 final, momentum 2 final. Looking at the picture, angles at all, or is everything in a nice straight line? Everything's in a nice straight line. So I'm not going to dulp. I'm not going to add vectors tip to tail, but I'm pretty sure that's coming up, I think, if I'm not mistaken, in our next example. It wants just to kind of compare the velocities. Let's, first of all, let's get this to that side. So this is really negative momentum 1 final equals momentum 2 final. And momentum is what times what? Mass times velocity. Okay, so this is going to be negative m1 v1 final equals, now what's mass 2? 2m v2 final. Okay. Oh, I didn't really need to put an M1. I think the M's are identical. One's M, one's 2M. Is there an M in everything? You know what? In this weird example, and I get this, negative V1 final equals 2 V2 final. Now let's interpret this. What's the fact that one's negative and one's positive telling me? First of all, it's telling me opposite directions. But what can you tell me about the mass that's twice as big and its velocity versus the mass that's half as big and its velocity? Here's what this is saying. The first can is twice as fast as the second can, but in the opposite direction. Here's our conclusion. Small can moves twice as fast, opposite direction. Which in hindsight makes sense. You got half the mass, you should get twice the speed. Well, twice the velocity since momentum's a vector. But there's a lovely algebraic proof. Now this bug's going, wait a minute, isn't this saying this one's twice as big? No, 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 read along with me. Opposite direction, the first can, velocity, is twice as big as the second can's velocity. The smaller can moves off twice as fast. Next page. Some terminology. The first two are important, the third one not as much. A completely inelastic collision, the masses stick together like the bullet and the block that we just did. And in those, momentum is conserved, but you lose some kinetic energy, a fair bit. In fact, you know how much kinetic energy we lost in the earlier example? 932 joules, because that turned into heat. Doesn't mean that energy isn't conserved. Overall energy is conserved, but kinetic energy is not conserved. A lot of your kinetic vanishes and goes into heat when they stick together. The second type of equation, I want you to scribble out the word partly. I'm just going to use the word elastic. The masses bounce off of each other, like curling rocks, like body checks in hockey. Oh, tackling in football is usually an inelastic because usually the tackler sticks to the tacklee. Hockey body checks. Now here's how I remember the difference between elastic and inelastic. I think elastic band, rubber bounces, bounce off each other. Inelastic, not elastic, not rubber band, not bounces, don't bounce off each other, stick together. And in an elastic collision, momentum is conserved. In fact, you'll notice momentum is always conserved. You lose some kinetic energy when you bounce off of each other, not as much as when you stick together. So there's some loss of kinetic energy. Total energy is still conserved, but some of it turns into heat. Then there's this weird, obscure one called perfectly elastic. And if I use that phrase, you need to be aware of it. I think it shows up in the homework. I think it's going to show up in your big unit review. Full disclosure, I'm not going to use it on a test, but I'm mentioning it because it's part of the learning outcomes. In a perfectly elastic, well, the masses still bounce off each other, but not only is momentum conserved like it was in the previous two, it turns out in this case you don't lose anything to heat. That's the definition of a perfectly elastic collision. The amount of kinetic before equals the amount of kinetic after. Now that can only occur with certain conditions. In a perfectly elastic collision, both objects have to have the same mass, and they rebound apart at a 90-degree angle. So if the question tells you it's perfectly elastic, you can assume the angle is 90 degrees. This one here is a little obscure, but I'll show you where we use it. For now, let's enter the world of angles. A 60-kilogram hockey player traveling 2 meters per second toward the north collides with a 50-kilogram hockey player traveling 1 meter per second towards the west. Okay, we have directions. Ding, 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 ding. This is going to be much tougher. The two become tangled together. They stick together, which means this is an inelastic collision. And it wants us to find the final velocity. By the way, magnitude and direction, because velocity is a vector. We start out the same way. Is this a collision? This is a job for conservation of momentum. The amount of momentum before equals the amount of momentum after. Before the collision, what's moving? Mass 1, mass 2, or both? Both. Stuck together or separate? Separate. momentum 1 initial, leave a space, plus momentum 2 initial, and I'm leaving a space because I know there's angles and I'm going to dulp, equals momentum after the collision. What's moved? Oh, sorry. Wham! They collide! Haha, hopefully I got you. After the collision, what's moving? Mass 1, mass 2, or both? Both stuck together or separate? Stuck together. Now, so far, nothing's changed from the first lesson. Now it's going to change. First of all, I see north, east, southwest. I'm going to throw compass rose on here because I'm not a foolish person. Are there angles or directions in this question? Dulp. Dulp. What direction is the first player traveling? North. Plus. What direction is the second player traveling? West. Now, what goes on these pictures? The momentum, because that's what's conserved. Momentum is what times what? Mass times velocity. I can do this one in my head. It's going to be 120 kilogram meters per second. Momentum is mass times velocity. This one's going to be 50. Now my scale is garbage because 120 is more than twice as long, so I'm just going to lengthen this like that. That equals the momentum of both. Now I'm not sure what that's going to look like, but as a picture, what's right here? A plus. Hey, how do I add two vectors together? Draw them tip to tail. I'm going to draw the 120 first. $120, and then I'm going to go west 50. By the way, common mistake, kids put the velocities on this. No, velocity is not conserved. What is conserved is momentum, and that's what lets me do this. Can you see the resultant? Here it is. This is the momentum of both afterwards. How can I find out how big that is? Hey, Pythagoras. 50 squared plus 120 squared equals, this one's going to work out evenly because I cooked the numbers. I get this. The momentum of both final equals 130. But that's not what this question asked me to find. This question asked me to find velocity. Well, how are momentum and velocity related? Momentum is mass times velocity. So if I want to find the velocity is going to be 130. The momentum divided by the mass of both. That's actually not the velocity. That's only going to be the speed. To get the velocity, I'll have to do a theta, get an angle. But right now, I can say the speed is going to be 130 divided by, how big was the first hockey player mass-wise? 60 and 50. $130 divided by, well, 110, 60 plus 50. They move off together with a speed of 1.18 meters per second. That's a speed. Now, how can I turn this into a vector velocity? I need an at. Let's go look at my picture here. You know what? Where is the vector originating from? Right there. That's going to be my theta. Can I use SOHCAHTOA here? Yeah, I used Pythagoras and SOHCAHTOA because there's a lovely right angle. So theta is going to be opposite, adjacent. Hey, it's going to be tan. What I'm doing in Hawaii right now. Oh, Mr. Du. Okay, sorry. Tan theta equals opposite over adjacent. How big is theta? Shift tan, opposite over adjacent. And I get an angle of 22.6 degrees. You could say 23 degrees. I'll go 22.6 degrees. At 22.6 degrees. What of what? North of south, east of west? What of what? West of north. And you can see the amount of work went way up, and that was for a right-angled question. Got to be honest, on your test, on your written section, I'm going to give you at least 2 of these, and they probably won't be right-angled. Oh, also, instead of 22.6 degrees west of north, I would also accept 90 minus that. I would accept 67.4 degrees north of west. That would mean you drew the 50 first, and then you added the 120. If you did that plus that to get that, this would be your theta right there, and I would accept that as well. So I would argue I'm not doing anything new. It's still conservation of momentum, but I'm combining vector math and conservation of momentum, and hopefully you're noticing being way more careful and way more paranoid. That was so much fun. Let's do another one. Huh. 10. That was too funny, Mr. Dueck. Too funny. Example 5. Just going to pause for a second. I'm kind of thinking about changing the order of the examples here. Hang on. Yeah, I'm going to say, first of all, turn to example 8, which is the last example before the homework. I like this question. I like this question. I like this question. I like this question. Now, this is my hideous diagram. I was doing this on a computer. It says, find the final velocity, magnitude, and direction of object B. So we're talking about curling rocks, where they bounce off each other at an angle, except the problem is, in real life, for curling rocks, the masses are identical, which would mean the masses cancel. So I've got different masses. This has a mass of 12.1 kilograms, traveling at 9.3 meters per second. This has a mass of 4.2 kilograms with a mystery velocity, and this has a mass of, 12.1 kilograms, traveling at 4.1 meters per second. And it looks like this bottom one has bounced off at a 51-degree angle. This is the kind of question I'm going to give you. Hopefully you can see, by looking at the picture, angles. Is there a collision? So we would start off, and we're going to need lots of room, so I'm going to start off here by saying the sum of all the momentum before the collision equals the sum of all the momentum after the collision. How much room did I leave? Okay, we may need to do some trig up here, but I'm going to write the rest of my work over here now. Before the collision, what's moving? Mass A, mass B, or both? Well, it does say that B's initial velocity is 0, so it's going to be momentum A initial vector. Wham! They collide. After the collision, what's moving? Mass 1, mass A, mass B, or both? Both. Stuck together or separate? Stuck together. No, separate. So it's going to be momentum A final plus momentum B final. Dolp. Here's momentum A initial. It looks like from the picture, go ahead, it's a terrible drawing. Looks like from the picture it goes straight sideways. Now, how big is this? Mass times velocity. It's going to be, and I'm not going to round off at all here because I'm going to be using this, it's going to be 12.1 times 9.3, 112.53. That equals, looks like mass A after the collision as a vector looks like that with an angle of 51 degrees right there. How big? Mass times its new velocity. 12.1 times 4.1. 49.61. Plus momentum B final. Well, looking at the picture, it looks like something like that. Okay. How would I add these two vectors together? I would draw them tip to tail. And here's the important thing. I know when I add these together what I'm supposed to get. I'm supposed to get a nice horizontal vector. I'm going to draw my triangle up here. So it's going to look like this. Here is the 49.61. Here is the 51-degree angle. Now I'm going to add momentum B final. I should have labeled that. I'm going to add that. When am I going to stop drawing? Not now, because if I stop there, these would not add to a horizontal line. These would add to something slanty. So that would be no good. Neither am I going to go this far, because that also adds to something slanty. I'm going to stop, go, right there. Here is momentum B final as a picture. And I know that the resultant is 112.53 because that plus that tip to tail has to work out to that. That plus that tip to tail has to work out to horizontal or east, whatever you want to call it. SOHCAHTOA? Nope. So, cosine law. What's the cosine law? This squared plus this equals this squared plus this squared minus 2, this, cos that. Say, what? Boy, I didn't leave you guys much room here. You might need to go on the next page or write small or something in hindsight. Okay, I'm going to zoom in so I can write small-ish. So the cosine law says this. Momentum B final squared, mystery momentum, equals 112.53 squared plus 49.61 squared minus 112.53 times, you know what, I need to move this over, minus 112.53, sorry, minus 2 times 112.53, good gosh, times 49.61, cos 51. Going to go to my calculator, making sure I'm in degrees. 112.53 squared plus 49.61. So avoid rounding these off if you can, squared. Minus 2 times 112.53 times 49.61 cos 51. I get, wow. Oh, that's momentum squared. How to get rid of a squared. Yep. Square root. I get 89.98. You know what? I get an even 90 if I go to 3 sig figs. I'll keep this on my calculator, but I'll write down here momentum B final equals 90.0 kilogram meters per second. Now here's the problem. That's not what the question asked me to find. It wanted me to find the final magnitude and direction. Well, if I know momentum, how can I find speed? Divide by the mass. How can I find velocity? Then do some trig and find the theta. Okay. If I divide by the mass, I'll get this then. Let's go to green, Mr. Dueck. the final velocity of B is going to be 90 divided by, what was the mass? 4.2? 4.2? Oh, use my answer button, Mr. Dueck. I get a magnitude of 21.4. At. Now this is a tough question here. What I think I want is this angle right here. I can't use this angle because this is not a north of south or a east of west. It's a slanty from a slanty. So that one there, even though I could find it, isn't going to help me. What I do want is this angle, because this is going to be north of east. I can even write that down. North of east. How the heck can I find that angle? Well, those of you that did foundations of math may recall, and I showed you this trick before, anytime you have a Z like that, this angle and this angle are the same as long as the top and bottom of the Z are parallel. So I'm going to find this angle, which is inside my triangle. And it's the same as this angle. Now, how will I find this angle? Can't use SOHCAHTOA. I'm going to use the sine law. Wait a minute, Mr. Dueck. I thought you only used the sine law when you had a pair. And I don't know both of those. I don't know both of those. Oh! I do know this now. It was 89.9869333. That. So I got a pair. I can use the sine law. Where the heck am I going to do the sine law? Well, it's a good question. I'm kind of running out of room here. I guess I'm going to kind of smoosh it in right in the bottom corner. This is terrible organization. What's the sine law? It says the sine of the mystery angle, theta, which is right there, divided by the side across from it, 49.61, equals the sine of the angle that I know, 51, divided by the side across from it. Now, I'm not going to use 90.0. I happen to still have this on my calculator. Now, if you don't have it on your calculator, but you divide it by 4.2, if you go answer times by 4.2, now you've got this number back. Hey, isn't that clever? Because that was the math. Anyways, I'm going to write 89.987. Cross multiply. 49.61 times the sine of 51 divided by answer button. That's the sine of theta. How can I find theta? Second function, sine, inverse sine, shift sine, 25.4 degrees. Wow. That's throwing everything at you all at once. That's throwing everything at you all at once. Now I want to go back and look at some of those that I skipped. By the way, when we get back from the break, lesson 6.5, after the break, it'll be just practicing this, practicing this, practicing this. So if you're finding this tough, it means you're normal. Let's go back and look at, example 7. A 10-kilogram curling stone is sliding along the ice when it hits a stationary, that's probably important, 18-kilogram bucket of sand. After the collision, the curling stone's velocity is 3 meters per second east, and the bucket has a velocity of 2.3 meters per second, 43 degrees south of east. What was the initial velocity, magnitude, and direction of the curling stone before the collision? Before the what? Before the collision. Before the what? Before the collision. This is a job for conservation of momentum. And you know what? I'm going to put a north, east, south west. I really should have done that on the previous question too, and I didn't. That might have bit me. Well, how much room do I have? I think we can pull it off. The sum of all the initial momentum equals the sum of all the final momentum. Before the collision, what's moving? The stone, I'll use S for stone. The bucket, I'll use B for bucket. Both or neither? The stone. Wham! They collide. After the collision, what's moving? The stone, the bucket, or both? Both. Stuck together or separate? Separate. Are there angles? Yep. Ding, 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 ding. I better gulp. So the initial velocity of the stone, oh, that's what they want me to find. After the collision, the stone is 3 meters per second due east. As a picture, it's going to look like this, but I'm not going to put a 3 here. What goes on here is not velocity. What goes on here is momentum, which is going to be mass times velocity. I can do that one in my head. 30 plus. It says the bucket has a velocity of 2.3 meters per second at 43 degrees south of east. South of what? South of east. South of what? South of east. South of what? South of east. Draw east first. What of east? South of east. How many degrees? 43 degrees. How big? Bucket, 18, times velocity, 2.3. 18 times 2.3. By the way, if you want to, you can always go 18 bracket 2.3 bracket equals, what did I say? 41.4. You can actually do the math right on the arm, and maybe that's a good idea. You know what? My 30 is too long compared to this, but this is not my final picture. Now, I don't know what this looks like yet, but I do know how to add this and this together. There's a plus sign. How should I draw them? You guessed it, tip to tail. So what's that going to look like? I'm going to try drawing it nice and big up here. It's going to look like this. 30, mass times velocity. 41.4, so that's going to be a little longer, maybe like that. 41.4. Oh, and they told me that this angle here was 43 degrees. What's the resultant? Which is, by the way, what I'm trying to find. From the tail of the first to the tip of the second, this must be the initial, not velocity, momentum of the stone. But the velocity will have the same direction. Oh, I need an angle in the triangle. Well, if this one is 43 degrees, this is going to be 137 degrees because it has to add to 180. Okay. Whew, I'm rethinking my spacing on this. I really should have gone 1 page per question instead of half page per question. And yeah, these are the big leagues. This is the tough guns. This is how it rolls in two-dimensional land. Cosine law. How do I know? Well, okay, it ain't SOHCAHTOA. No right angles. Do I know both of those? Nope. Do I know both of those? Nope. Do I know both of those? Nope. I know that, but that's what gave me that. That doesn't help me fill in anything. This is the cosine law. What's the cosine law going to say? Where am I going to write that, Mr. Dueck? I guess kind of right in here. You know what? Let's zoom in again. Use that trick so that I can write smaller, but you guys can still see. It's going to be the momentum of the stone initial squared equals 30 squared plus 41.4 squared minus 2 times 30 times 41.4 cos 137. 30, clear, 30 squared plus 41.4 squared minus 2 times 30 times 41.4 cosine 137. Double check to make sure I didn't make any typos. I don't think I did. Hope I haven't made any typos in this lesson. Believe it or not, I did half this lesson and then I found out I'd done the very first one, the bullet block question, wrong. So I'm teaching this for the second time. What the? Oh, that's momentum squared. How to get rid of a squared? Square root. The final, the initial, because there's an I here, the initial momentum is 66.563. I'll carry that many sig figs. The initial momentum is 66.563. You can carry a few more if you want, because this isn't what I want to find. That's the initial momentum. Now I need to get a velocity. Okay. The velocity is going to be 66.5656, Mr. Dueck, 3 divided by the mass, because if momentum is mass times velocity, then velocity is momentum divided by mass. What was the mass of stone 1? 10. Hey, I can do that in my head. It's going to be 6.656, okay, 6.66 meters per second. At, I need a direction. There's where we're starting. What of what? North of south, east of west? What of what? South of east. Can fill that in. How big is theta? How can I find theta? It's going to be the sine law, because now that I know this momentum, I've got a pair that 137 goes with this. Heck, I'll do the sine law way up here. This is terribly unorganized, I realize. It's going to be this. The sine of 137 divided by the momentum that was across from it, which was 66.563. Again, make sure you use the momentum here, not velocity, because momentum is what's conserved. That's what I'm going to use in all my work. Then at the very, very end, I'll divide by the mass to get the velocity. Equals sine of mystery angle theta over 41.4. Hey, again, this is one fraction equals one fraction. I'll get sine theta equals 41.4 times, this will move diagonally, right? Sine, whoop, don't write sine twice, 137, all divided by 66.563. Now, if you had divided by the mass, which was 10, I did it in my head, if you had done that and you want to get your answer button back, just multiply by the mass again. There's our original momentum. It's going to be 41.4 sine 137 divided by answer button. Ha-ha. What the? Oh, that's the sine of theta. Shift sign to find theta. Shift sign of the answer. And I get 25.1 degrees. South of east. I like this question. I like this question. You know what? There's going to be at least one of these on your test where there's an angle where you have to use the cosine law. And this will be worth 7 marks. By the way, in case you're wondering, usually I give 1 mark for that. Usually I give 1 mark for that. 1 mark for the triangle. You're up to 3. 1 mark for that, you're up to 4. 1 mark for that, you're up to 5. 1 mark for that, you're up to 6. And 1 mark for that, you're up to 7. Usually something like that. Okay. Whew. I'm going to come back to example 6. Let's do example 5. Maybe not. I might pause here. Hang on. Let me rethink this. So we'll finish off with example 6. We'll do the explosion another day, although it's pretty cool. Example 6 says a 5 kilogram puck A, moving at 1.2 meters per second. Yeah, I just took a question from a different diagram and changed it, in case you're wondering. Collides obliquely. The word obliquely is a fancy word for at an angle like that. Not straight on, not head on. So if it was a head-on collision, that's not an oblique collision. With an identical stationary puck, puck B then moves at 0.9 meters per second, as shown. Final velocity, magnitude, and direction of object A. Is there a collision? Yeah. Hey, this is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. Before the collision, what's moving? Mass A, mass B, or both? Well, it says mass B is stationary, so momentum A initial. And they collide. After the collision, what's moving? Mass A, mass B, or both? Both. Stuck together or separate? Separate. Look at the picture. So I'm going to have momentum A final combined with momentum B final. And now we pause. Look at this question. Are there angles? Yep. You know what? Let's even put a little north, east, south, west. Because we have angles, I'm going to dope. A initial, looking at the picture, looks like this. And it has a mass of 5, a velocity of 1.26. A final looks like this, equals. And this is momentum A final, and it's the mystery. Momentum B final looks like that. And it has a mass of 5 as well, because it says the pucks are identical, times 0.9. You know what? That's 4.5 kilogram meters per second. How am I going to figure this out? Well, I can add these two together, tip to tail, and I know what the answer looks like. When I add this plus this, I'm supposed to get a horizontal line of 6. That's going to tell me how to draw this. I'm going to start out drawing mystery momentum A, momentum A final. I'm going to then draw B, and I know not to draw it that far because that won't give me a resultant that's dead horizontal. And I know not to draw it this far because that won't give me a resultant that's dead horizontal. I know to draw it about there. And it tells me that this, 4.5, and I know that this is 6. I need to get an angle. Well, it said if you draw a horizontal line and then go down to B, that's 29 degrees. If I draw a horizontal line and I go down to B, that's 29 degrees. How's that help? Hey, here's that Z trick again. You're going to be using that fairly frequently. If you have a Z, this angle and this angle are the same. So this is 29 degrees. Is there a right angle? Not sure. Don't think so. Doesn't look like it. So I'm going to fall back on the cosine law. Momentum A final squared equals 6 squared plus 4.5 squared minus 2 times 6 times 4.5 cosine 29. Six squared plus 4.5 squared minus 2 times 6 times 4.5 cos 29. Oh, square root. And I get, oh, almost exactly 3. I'll carry some extra sig figs because this is not what I want. This is the momentum. I want the velocity. So I'm going to write 3.0034. Momentum A final equals 3.0034. Now, to find the velocity, divide by the mass. I'll do that down here. Velocity A final is going to be 3.0034 divided by 5. It's going to be divided by 5. Oh, almost exactly 0.6. 0.6001. Sorry, 0.6001. 0.601 meters per second at, by the way, I want to use momentum for the sine law, so I'm cleverly going to go times by 5 to get my momentum back, or you could have used 3.0034. If you go to about 5 sig figs, you'll be safe with the sine law, cosine law stuff. Speaking of, I want to find the angle. I guess it's going to be right here. What of what? I think it's going to be north of east. How big? Hey, I got room to do the sine law up here. Boy, have I been disorganized. Sine theta over what's across from it, 4.5, equals sine of 29 over what's across from it, which is 3.0034. Once again, I think I'm going to times the 4.5 over. I'll get 4.5 sine 29 divided by, I'll use my answer button. Now that's the sine of theta, inverse sine, and I get 46.6 degrees. Whew! Wow. Like I said, this may be, you know what? I think I said it was among the top 5 toughest lessons of the year. I'd put it top 3. Top 3. Top 3. We're going to practice this and practice this and practice this, and you will get the hang of this. For now, I have a take-home quiz for you to work on. It's not on angled momentum. It's all on straight line, linear momentum. Well, first of all, let me also talk about which questions in theory you can do. You can try number 1, that's in a nice straight line. You can try number 5, that's at an angle. 4 says write equations for horizontal and vertical momentum. B, find the unknown speed and direction. C, find the you know what? I've decided I don't mind this question. I just don't like the way the answers are phrased because it's using components and I'm nudging you to get past components. Can we do 6? Oh, 6 is ugly. You know what? I'm just going to give you 5 right now, and I'm going to say your other homework is, here is the take-home quiz. This is all linear. So we have tackling, football, and impulse, tackling, football, and impulse, all straight line, all straight line. This is going to be due after we get back. Your other homework is get anything that you haven't finished. Okay? Hey, have a good break. Next lesson, bring homework from another class if you want. You can work on it. And also, I have a cool physics video that I think you'll find interesting. You can watch that. I think your inner nerd will think it's pretty cool. Oh yeah, and Merry Christmas. Have a wonderful break and a happy